So next we're going to talk about section 10.9 in chapter 10, flow and conduits. And we're going to talk about non-round conduits. And we are going to use as our relevant dimension either the hydraulic diameter or hydraulic radius. And we need to know what those terms mean and how to use them. It's quite easy. So let's scroll way down to the end of the chapter here now and get to section 10.9 and jump right in. This is a pretty simple section. It's going to be pretty quick. Conduits can be made in different shapes and they can be square or rectangular. So we need a method for dealing with the equations, the appropriate equations for this. Examples might be that you may have seen are square or rectangular ventilation systems in buildings. If you've ever looked into the ceiling of an office building, for instance, you see these sheet metal ventilation tubes, conduits that are usually rectangular, or open channel flow. Some good examples are irrigation channels that you may have seen, and those may not even be rectangular. They may be more shaped like this with sloped boundaries. There are some of these in Boise, Idaho, and certainly across certain sections of eastern Washington. And so irrigation canals or perhaps spillways of dams, or in the case of a ventilation system, you might have that system being completely filled with material all the way to the edges. So we need a way of dealing with non-round conduits. And the way we do that is to apply the Darcy-Weisbach equation, but instead of using the diameter of a circle, we're instead going to use what's called the hydraulic diameter, d sub h. And that is going to be defined as 4 times the cross-sectional area divided by the wetted perimeter. And what do we mean by the wetted perimeter? Let's take the example of a rectangular ventilation channel where this is completely filled with a gas from edge to edge. I'm not doing a very good job of drawing this, but it's completely filled with gas. And it has some length to it in this dimension and a width to it, let's say. And so to calculate this, the cross-sectional area, of course, is just the area is just the length times the width. And the wetted perimeter, since the gas is filling this ventilation channel all the way around the entire perimeter of this conduit, the wetted perimeter dH, the hydraulic radius, is going to be 2W plus 2L. Okay, and I believe that's shown on the next page here. We can then simplify that hydraulic radius to be hydraulic diameter to be 2LW over L plus W. Check our units. The units of this on the top are going to be, for instance, meters squared or length squared over meters or length. And this cancels that, and we're left with basically a length. So the units work out, and so when we plug this into our non-dimensional numbers, we're going to get the right units. Some other examples, let me go to the next page and do some other examples. So another example might be an open channel, that looks like this, just a rectangular channel. In this case, we might have a depth, D, and a width, or we could have called it a length as well, but in this case we'll just call it a width. And so in this case, the cross-sectional area is just dW, but the wetted perimeter, the D, you know what, I did that wrong back here. This is not D sub H. This is the wetted perimeter. D sub H is the cross-sectional area over the wetted perimeter. So here we're going to be calculating the wetted perimeter, and it's in this case going to be 2 times the depth plus just 1 width, because the fluid is only in contact with these 3 sides. And so that is the wetted perimeter for this particular case, and we would divide that into the 4 times the cross-sectional area to give the hydraulic diameter. So it's pretty easy to do as long as you know the geometry and you can figure out basically the lengths of these wetted sides. And then it's important to note that it's not as accurate when we use the hydraulic diameter as it is when we use the Darcy-Weisbach formula for true circular conduits. We can only expect laminar flow to be plus or minus 40% accurate, which is not really that good. However, when we use the Swamy-Jain formula for turbulent flow, we're good within 15%. And since most of our cases are actually turbulent, we're not incurring too much error in determining the friction factor and therefore the head loss when we when we're forced to use a hydraulic diameter for non-round conduits. So that's it for this section. Okay, thank you.